Alright, so I just wanted to start off with kind of a definition of orbital motion, and the way I tend to think about this is the central of the bodies I call the larger mass, so I call it capital M, and then the smaller of the bodies I call it little m, and then the premise here is that there's, some kind of orbit going around, and then the radius of the orbit we're going to call r. And I think that gets us pretty much everything we need to do the rest of the derivation here. So all of these orbital motion equations start with the premise that centripetal force is caused by centripetal force is equal to centripetal acceleration is caused by the gravitational force, so the centripetal force equals the force of gravity calculated by Newton's universal law of gravitation. And we know that centripetal force equals mv squared over r, where the m is truly the object that is doing the orbiting, versus gravitational constant, big M representing the mass of the larger of the two, little m representing the mass of the smaller of the two. I know a lot of times this equation is given as m1, m2, but I always have a hard time keeping the ones and twos separate, so I like doing it this way, over r squared. Okay. So a couple of things can happen here. So alright, so anyways, one of the r's cancels out, mass cancels out, and that leaves us with v squared equals gm over r, where mass is the mass of, I guess, the planet or whatever is the central, more central of the two bodies there. And then we can solve for v. So just take the square root, so v equals square root of gm over r. Now, it's not uncommon, so this is frequently what we would call the orbital velocity equation. That's nice. It's very useful. It'll be used for a lot of things. But if you need to solve for something else, most likely the radius of a particular orbit, sometimes it is helpful for you to remember that velocity equals circumference over period. And maybe also helpful for you to remember that circumference equals 2 pi r and over t. So that can be a helpful substitution. Now let's do some algebra with this. So I'm going to substitute in place of v in this equation. I'm going to substitute 2 pi r over t. And I'm going to go ahead and get this gm over r out of the out from under the square root. So I'm going to go ahead and square all of this. Gm over r. So 2 squared is 4 pi squared r squared over t squared equals gm over r. Cool. Oh, too far. There we go. Where to go from here? If I want to solve for r, maybe I could cross multiply here, and I would get 4 pi squared r cubed equals gmt squared. So there's some Kepler's law like things going on there. And if I further wanted to actually solve for r, I can move the 4 pi over 4 pi squared, I do really well in this derivation if I make it through without dropping off a square from something somewhere along the way. But anyways, there goes that. And then we'll just cube root everything, and so we'll get R equals cube root of GMT squared over 4 pi squared. And that's not the only way that you can write this equation, but that's one way that you can write this equation. And it's very useful if you need to do something like solve for the orbital radius of a geosynchronous satellite, or the orbital radius of any satellite for that matter. So hope you found that helpful. And just to be consistent with the other, let's give that thing a circle. All right. Also, this equation, if you know the radius, you could also solve for time instead of, or period instead of radius. Oh yeah, by the way, to be dimensionally consistent, with G, mass has to be in kilograms, radius in meters, and period in, that's right, seconds. So, very frequently you're given a unit of time other than seconds, so you will have to convert that unit of time to seconds, and that will make things work out much more nicely for you.